Welcome to This Explainer. Today, we're diving into the broken physics mystery, rewriting the cosmos. You know, the physics you probably learned in high school, the foundational rules of our universe? Well, they're kind of starting to fall apart. For decades, we've relied on this standard rulebook to explain literally everything, from how stars are born to the darkest corners of space. But recently, a massive wave of new, unprecedented data just threw a huge wrench into all of it. Let's get right into it.
So, what happens when the most precise measurements of the universe completely break our understanding of physics? It's like a crazy detective story. We've got the most advanced telescopes in human history right now, but we're facing this totally bizarre reality. The sharper our lenses get and the more precise our measurements become, the blurrier the actual picture of physics gets. It's wild. To understand why physicists are literally hitting the panic button right now, we first need to look at the baseline we're working from.
Okay, let's ground ourselves with the cosmic blueprint. It's honestly amazing we even have a timeline for this. In the first single second, cosmic inflation happens and the fundamental forces separate. Fast forward to 380,000 years, and recombination allows the very first atoms to form, which releases that famous cosmic microwave background radiation. And then, around 100 million years in, gravity finally condenses massive clouds of gas to form the first stars and galaxies. This specific timeline is our standard model. It's basically the sacred text of modern physics, which is exactly why the anomalies we're about to talk about are so incredibly shocking.
But, before we get too confident in that standard model, let's look at the universe's makeup. This really highlights how little we actually know. Ordinary matter, the stuff that makes up you, me, the Earth, your coffee cup, that's only 5% of the cosmos. Just 5%. The rest is completely dwarfed by 25% dark matter and a whopping 70% dark energy. And let's be real for a second, dark is just a polite scientific placeholder for we have absolutely no clue what this stuff actually is. 95% of the universe is essentially invisible. And this huge, intimidating unknown is exactly where our standard models are starting to buckle under the pressure.
So, let's talk about our first major issue, the Hubble tension, a crack in the macro scale.
Right, so we're looking at a glaring alarm bell here. We've known for ages that the universe is expanding, but when astrophysicists try to measure exactly how fast, the numbers just don't match up. Traditionally, scientists used a distance ladder. Imagine guessing the distance of a streetlight down a dark road just by how dim the bulb looks and using that guess to measure the next light. It's kind of shaky, right? Well, in early 2026, researchers introduced the local distance network. This replaced that old fragile ladder with a massive interconnected mathematical framework. They combined independent distance indicators all at once, things like Cepheid variables, which are basically pulsing stars that act like cosmic yardsticks, along with type 1a and type 2 supernovae and Mira variables. By transparently assessing the whole system and accounting for shared uncertainties, they achieved an incredibly reliable measurement of the universe's expansion.
And the number they got from this sturdy network? 73.50. That's 73.50 kilometers per second per megaparsec. Now, they reached a precision of just over 1%, which is an absolute mathematical triumph. But here's why this number is triggering a full-blown crisis. When we measure the early universe using that cosmic microwave background radiation we talked about earlier, the expansion rate comes out to about 67. To put that into perspective, it's like your GPS calculating that your morning commute will take exactly 67 minutes, but every single time you drive it with a perfectly calibrated stopwatch, it takes exactly 73.5 minutes. It's not a rounding error. These new local measurements disagree with the early universe models by 5 to 7 standard deviations. In the physics world, that translates to a 1 in a million chance that this is just a fluke. The discrepancy is absolutely real.
This isn't just some minor math update either. The collaboration firmly stated, and I quote, "This work effectively rules out explanations of the Hubble tension that rely on a single overlooked error in local distance measurements." Let that sink in for a second. By ruling out a simple mistake, it strongly suggests we are missing a fundamental piece of physics that sits entirely outside of our standard cosmological model. Our understanding of the macro universe is just flat out incomplete. Which brings us to our next major issue, the black hole paradox, a crack at the extreme scale.
Okay, so the universe isn't just breaking down on the massive macro scale, we're also seeing standard physics completely shatter at the most extreme micro scale imaginable. the dead center of a black hole. For decades, classical general relativity has told us that matter is crushed into an infinitely dense singularity, a point where the laws of physics just completely break down and trapped information is permanently lost. That's a huge headache, usually called the information paradox, because quantum mechanics says fundamental information can never actually be destroyed. But now we have loop quantum gravity offering a totally mind-bending alternative. It suggests matter actually hits a Planck scale density limit. Think of it like compressing a super tight spring until it physically cannot compress anymore. Instead of vanishing into nothingness, it experiences quantum repulsion, bounces back, and ultimately escapes, completely preserving that cosmic information.
And this brings us to a really thrilling concept from a 2026 paper trying to fix these rules. It's called a Fuzzy-Novae. The formal definition is a bit of a mouthful. A time-like ejection of an entire stellar mass from a macroscopic black hole driven by a localized quantum gravitational bounce that bypasses the standard Hawking evaporation paradigm. But let's translate that into plain English, right? It basically means that instead of a black hole just sitting out there forever, slowly evaporating away through Hawking radiation, it eventually acts like a massive, delayed cosmic bomb. That quantum bounce inside forces the black hole to dramatically eject all of its internal matter right back out into space.
Let's trace the actual physics of what's happening here. Imagine the massive core of a dead star collapsing under its own unimaginably crushing gravity. It gets denser and denser until it hits a fundamental wall in the fabric of the universe, that critical Planck threshold. The matter literally cannot get any smaller. At that exact microsecond, quantum forces step in and essentially say, nope, that's enough. The collapse abruptly halts, and local quantum repulsion triggers a massive bounce. It's wild to think about, but the math shows this collapse turning instantly into an outgoing solitary wave of matter.
And when you look at the space-time diagram of this event, it reveals this localized white wave region. It's essentially a temporary anti-trapped zone. In simpler terms, it's a cosmic escape hatch. All that trapped information and matter that classical physics thought was doomed forever to a dark, infinitely dense point suddenly gets a backdoor. It uses this temporary exit path to safely escape outward, entirely bypassing the black hole's infamous event horizon.
So, to summarize the end of a macroscopic black hole, quantum gravity gives us 4 spectacular steps. First, stellar matter collapses and the core density approaches the Planck scale. Second, local quantum repulsion triggers a bounce, creating that dynamic anti-trapped escape hatch we just talked about. Third, a stable, solitary matter wave forms, carrying the mass outward. And finally, the entire stellar mass is violently ejected in a completely singularity-free path. This is huge. It means black holes aren't these eternal, bottomless pits. This elegant mechanism beautifully solves the messy information paradox that frustrated brilliant minds like Stephen Hawking for decades.
Which leads us to our final thought: rewriting the cosmos.
When we step back and look at the big picture, the takeaway is absolutely undeniable. From the macro-scale expansion problem of the Hubble tension all the way down to the extreme quantum depths of a bouncing Fuzzy-Nova, it is crystal clear that the universe is far more complex and dynamic than classical physics ever anticipated. So we're left with this massive question to ponder. Could everything really have formed from nothing, or are we on the precipice of discovering a completely unknown part of physics? As our measurements get sharper and our theories get bolder, keep an open mind, because the ultimate rulebook of the cosmos is definitely still being written. Thank you so much for joining me for this explainer, and I'll catch you next time.